My name is Levi Lynch, and today I'll be discussing the paper Beyond Regular Grids, Fourier-Based Neural Operators on Arbitrary Domains, presented at the 41st International Conference on Machine Learning. First, let's define exactly what is neural operator learning. Typically, we start out with some continuous data described by a set of partial differential equations. This is usually something related to real-world phenomena that we would like to understand. To solve these on a computer, we have to construct some sort of discrete model of the system, breaking it down into a set of points or cells. Then we use some sort of solution scheme, such as finite element analysis, to act as an approximation of our PDEs, evolving them in time. The two states are related by an operator. Therefore, we refer to this process as operator approximation. Finally, we have an estimate of what the evolved system should look like in our discrete space, and we can interpolate these to understand what happens in the continuous or real-world case. Neural operator learning uses a deep learning model trained with the objective to make a prediction with a minimal difference to those of a numerical model or real-world data. Already, this technology is being applied to solve some of the most challenging problems that we're facing these days. For example, predicting the pathways of hurricanes at a fraction of the computational cost of traditional numerical techniques. One approach which has gained a lot of traction recently is the Fourier neural operator, named so because it relies on Fourier transforms to understand global features, essentially learning how the PDEs of the system behave across the entire domain. The Fourier transform in this case is computed via the fast Fourier transform algorithm, which ensures that it's efficient and is able to scale well to a large number of points. However, the FFT algorithm has an important restriction. It's assuming that all of the points lie on an equispaced regular Cartesian grid. This might not be limiting for some problems, but if we're working with other geometries, it can be a major restriction. So, if we'd like to come up with an approach that is able to be applied to data that might be collected from real-world sensing locations which aren't equispaced, or if we're working on problems with other geometries, such as spherical rather than toroidal, it's helpful to think of another approach to tackle this Fourier transform while ensuring its ability to scale. To come up with a transform approach which suits our needs, we can go back to the foundation of the fast Fourier transform, which is known as the discrete Fourier transform. If we assume that we have discrete data x with points 0 through 7, we can calculate the discrete Fourier transform using this equation. Essentially, all it does is construct a set of sinusoidal basis functions from low to high frequencies, and then compute the amount of overlap between a given basis function and our points. If the overlap is low, then the Fourier coefficient associated with that frequency is small. On the other hand, if the overlap is large, then the Fourier coefficient is also large. This process is repeated for all the basis functions. Typically, this is an O(n) squared process where n is the total number of points. Too expensive to be feasible for most problems. However, neural operator learning is a special case. Instead of computing as many frequencies as points, we only compute the Fourier transform of a specific number of frequencies, m. This number m is much smaller than the number of points, and it is fixed. That is, it doesn't grow as the number of points grows. Therefore, the computational complexity of our algorithm is only going to grow linearly with the number of points. So from here, it's possible to introduce an additional term into the discrete Fourier transform, which is going to keep track of the locations of the points. This allows us to simply extend our evaluations to any arbitrary distribution of points, even for higher dimensional problems. And by arranging these into a matrix, we can quickly and stably compute the transform from spatial to spectral data just by using a matrix vector product. Because the number of modes is so low, this matrix vector product is actually more efficient when deployed in neural operators than the fast Fourier transform algorithm. Making this simple change allows us to tackle new problems or new variations of older problems. Even if our data is on a regular Cartesian grid, we can use our resources better by focusing computational power on areas of interest, for example, a specific part of the globe. The end result is a more accurate prediction computed in just a fraction of the time. Likewise, we can follow the same approach but use different basis functions to apply neural operators to new geometries, such as the sphere. Whereas previous approaches were limited to the distributions of points which they could effectively handle on a sphere, the proposed approach is able to handle any arbitrary distribution of sample points. Thanks a lot for checking out this video. If you'd like to learn more about this work, please feel free to look into the paper, which is openly available on arXiv, or look into the code and try out some of the experiments yourself with this link to our GitHub repo.